Hello everyone, welcome back to Layouts Tutorials. In this video, we are going to tackle about and solve some problems regarding with the chapter 6, gas and vapor power cycles and thermodynamics. So first, let's define what is a gas cycle. A gas cycle, as the name implies, is one in which the working fluid is a gas. Power cycles that operates with gas as the working fluid are used in reciprocating petrol engines and gas turbine engines, or what we call the diesel engines. The gas used as the working fluid within these engines is air. What is vapor power cycles? The vapor power cycles are used in steam power plants. In a power cycle, heat energy released by the burning of fuel is converted into work, or the shaft work, in which a working fluid repeatedly performs a succession of processes. In a vapor power cycle, the working fluid is water, which undergoes a change of phase. So as you can see in this image, this is an example of a diesel cycle, which is a thermodynamic process that is commonly used in diesel engines for internal combustion. Yes, as you can see here. It operates on the principle of constant pressure combustion and consists of four distinct processes: the intake, compression, combustion, which it banks, and the exhaustion, or the exhaust. So in this process, suction takes place at state 1 to state 2, and from state 2 to state 3, this process is called the adiabatic process. This takes place the compression, and both the inlet and exhaust valves are closed, and the compression takes place, which is much higher than that of an Otto cycle, and this increases the pressure and temperature inside. At state 3 to 4, the isobaric process, fuel is added, and the combustion occurs due to high temperature and while maintaining a constant pressure because the volume is also increasing. So while at state 4 to 5, the adiabatic process also, in this process expansion takes place. Due to combustion, the piston moves from TDC, top dead center, to BDC, or the bottom dead center, and power is generated. So from 5 to state 2, the isochoric process. In this process, heat rejection is taking place at constant volume. So that is what we call, or the exhaust. So here we have also an example of a vapor power cycle, or which is a Rankine cycle. Rankine cycle is the process widely used by power plants such as the coal-fired power plants or nuclear reactors. So in this mechanism, a fuel is used to produce heat within a boiler, converting water into steam, which then expands through a turbine, producing useful work. The steps in the Rankine cycle, as shown here, the corresponding steps in the pressure volume diagram are outlined. So I'm going to show you the pump here, compression of the fluid to high pressure using a pump. This takes work. Yes, into the boiler. The compressed fluid is heated to the final temperature, which is at boiling point. Therefore, a phase change occurs from liquid to vapor, steps 4 to 1, just here to here. And then in the turbine, expansion of the vapor in the turbine, steps 1 to 2. And the condenser, condensation of the vapor in the condenser, where the waste heat goes to the final heat sink, the atmosphere, or a large body of water, for example a lake or a river. 2 to 3. So that's more about the gas and the vapor cycle. So let's proceed on the problem solving. This is the example number 1 of the gas and vapor power cycle. Example number 1. A utility runs a Rankine cycle with a water boiler at 3 megapascal, and the cycle has the highest and lowest temperatures of 450 degrees Celsius and 600 degrees Celsius respectively. Find the plant efficiency and the efficiency of a Carnot cycle with the same temperature. So the pressure, so the property table will be significant in answering this problem. So the pressure, enthalpy, and this specific volume at state 1 are determined from the given temperature and in the saturated liquid values from our property table, which is here. I highlighted it to make sure. And so the enthalpy at state 2 will be determined from the energy balance on the pump. So we have the enthalpy at state 2 is equal to this enthalpy at state 1 plus the specific volume of saturated vapor multiplied by the pressure at state 2 minus the pressure at state 1. So yes, the enthalpy at state 1, which is here, is 251, yes, which is correct, plus our specific volume, which is here, which is 0.001017, which is here, which is correct, multiplied by our pressure at state 2, which is 3 megapascal or 3000 pascal, or 3000 kilopascal minus the pressure at state 1, which is 20 kilopascal kilojoule per kilogram. So we have 254.14 kilojoule per kilogram. So now the enthalpy at state 2 is determined from the energy balance on the pump, which is 254.14. So now the enthalpy and entropy at state 3 are determined from the given pressure and temperature with the separated water values from our, which is from our property table. We have the enthalpy at state 3, which is 3,344 kilojoule per kilogram, and the enthalpy at state 3, entropy 7.0833 kilojoule per kilogram degree Kelvin, which can be found here. I also highlighted it, table A6 at 3 megapascal. Which is correct. So now by finding the quality at state 4, we need also to use the property table, and the quality at state 4 is determined from the condition of the entropy of state 4 is equal to the entropy of at state 3, and the entropies of the constituents at the given minimum temperature taken from our property table, which is I also highlighted here. We have this equation na quality at state 4 is equal to the entropy at state 4 minus the entropy liquid at 60 degrees Celsius over the entropy evaporation at 60 degrees Celsius, which is here, which is correct. We have 7.0833 minus 0.8311 over 7.0784, and we have the quality at state 4 0.883. And the next process is to by finding that enthalpy at state 4. So by plugging that what we have, the enthalpy at state 4 is equal to the enthalpy liquid at 60, which is 251.18, which is correct, plus 0.883, which is our quality at state 4, multiplied by our enthalpy evaporation at 60 degrees Celsius, which is 2358, which is correct, 2358 or 2357.7, which converted to 2358 kilojoule per kilogram. So by plugging this into our calculator, we get 2333.65 kilojoule per kilogram. So by finding the efficiency of a plant, we can directly determine from the network output and the heat input. So enthalpy at state 3 minus the enthalpy at state 4 minus the specific volume of a liquid, multiply the pressure at state 2 minus the pressure at state 1 over the enthalpy at state 4 minus the enthalpy at state 2. So by plugging those that we get from our property table, we get the efficiency of a plant 0.326 or 32.6%. And the thermal efficiency of the Carnot cycle is determined from the lowest and highest temperature in the cycle, which is the 450 degrees Celsius and 60 degrees Celsius, and we need to convert this one so that we have this 333 from 60 degrees Celsius to degree Kelvin, we get 333, and from 450 degrees Celsius to degree Kelvin, we get 723 Kelvin. So the thermal efficiency of a Carnot cycle is given as this equation: 1 minus T1 over T3, or the temperature at state 1 over the temperature at state 3. 1 minus temperature at state 1, which is 333, over the temperature at state 3, which is 723 Kelvin. And by plugging this into our calculator, we get 0.539 as the efficiency, or 53.90%.